This section of the lecture notes is going to deal with the nutrient role in bioenergetics. You'll probably find the first quarter, maybe 25 to 30% of the notes to be review, hopefully, based on other classes in physiology or maybe even physics or something like that, or even exercise physiology. So some of you may be enrolled in that class right now or already have taken it, or many of you may not have taken that already. So with this section, we're going to look at nutrient role in bioenergetics. So when we're looking at nutrients, we're looking at macronutrients, of course, and then micronutrients as well. And that'll be my focus in this class, is to really introduce the role of micronutrients into these enzymatic processes. And so make sure you pay special attention to that. So bioenergetics. So bioenergetics just refers to the flow of energy within a living system. So we have to take in macro and micronutrients. We have to digest and absorb them. Then we have to use them for activity. So with the exercise science program, of course, we focus on muscular activity and even different training strategies to kind of stress these various bioenergetic pathways to produce ATP. So just some basic definitions here. So we know energy is just the capacity to do work. Then we have aerobic and anaerobic sources of ATP, right? Adenosine triphosphate. So aerobic just implies that the reactions within that area or within that pathway require oxygen. Anaerobic reactions do not require oxygen. Okay, and then we can have a mixture of both. At the bottom there, hopefully that looks familiar to you. That is the electron transport chain there. And so let's get my laser pointer out. And so it shows you the different cytochromes and starts introducing some various pathways to you, where maybe if you've seen the electron transport chain before, you know that oxygen serves as the terminal electron acceptor, where you get basically water and ATP. Okay? So we'll talk more about those specifically later on. A little bit of review about energy and the laws of thermodynamics. So the first law is energy is neither created nor destroyed. So we have to balance out equations, right? So if you were doing a chemistry class and you were showing reactions, you would be able to balance out all the products involved and account for those. There's basically about 6 forms of interchangeable energy states. Now, a physicist may have a different opinion here, but this is what we'll go with this class. Chemical, light, electric, mechanical, heat, nuclear, and then of course we'll focus on mechanical, heat, and even chemical reactions here. And of course the ATP that we need to fuel those reactions. And for us, we'll kind of focus on muscle physiology too, or refer to it anyway, where actin and myosin are allowed to have a cross bridge, and then ATP is used to drive those cross bridges and subsequent muscle contractions. So photosynthesis and respiration, they're kind of the opposite of each other, right? So if you've had another physiology in the class, they may have defined photosynthesis and respiration maybe a little bit differently, but the same idea is still there. So during photosynthesis, chlorophyll absorbs radiant energy from the sun to synthesize glucose from carbon dioxide and water, and then releases oxygen. And what we do as human beings, we undergo respiration, where we use oxygen to break down glucose, for instance, to provide energy for our body. So it's certainly a balance there in terms of photosynthesis and respiration, just with daily life and daily living. So for biologic work, really takes one of about 3 forms. One is just mechanical work, which we kind of highlighted before, and that's just actin and myosin having their cross bridges and be able to have a muscle contraction. There's chemical work for synthesizing cellular molecules, for instance, condensation. There's even maybe sodium. There's transport work as well that concentrates diverse substances in body fluids. So, for instance, in order to build up concentration gradients, so for instance, we have a concentration of sodium here on the outside, potassium on the inside, we have to burn ATP to be able to establish those concentration gradients. And so an example of the transport work is the sodium potassium ATPase pump. So we need ATP. We need to be able to generate ATP through various sources, both anaerobically and aerobically, so that our system remains flexible regardless of circumstance. So potential and kinetic energy. Potential energy is just energy associated with a substance's structure or position. It's stored energy. It can be described as stored energy a lot of times, especially when we're talking about macronutrients. Then we have kinetic energy. It's just the energy of motion. So a muscle contraction is probably the easiest example for that. Then the total energy is the sum of potential and kinetic energy. Potential energy available and kinetic energy that's being used. So releasing potential energy transforms it into kinetic energy of motion. So we need to be able to take the fat storage or the carbohydrate storage and be able to unlock that potential energy to do biologic work, such as muscle contractions, transport, and chemical work. One reaction you need to get to know is a redox reaction. Now, a redox reaction is actually two reactions in one. It's reduction and oxidation. So oxidation is when a substance loses electrons. Okay, so remember, an electron is negatively charged. So if I lose an electron, I become more inherently positive. If I gain electrons, I become more inherently negative. So reduction is when a substance gains electrons, it becomes more negative. So, for instance, the addition of hydrogens. And so that'll become important when we're talking about these bioenergetic pathways. Because we are aerobic beings and we need to take NADH and FADH to get to the electron transport chain, that's going to be important to talk about those things. And even in creating other substances like lactate, we need to be able to watch the hydrogens and their related electrons to be able to fully understand the conversion of, say, pyruvate to lactate. So redox reactions power the body's energy transfer processes and describes this coupled reaction. And so this is a simple reaction where pyruvate is actually a product of anaerobic glycolysis. When we need energy or ATP very quickly, we need to engage in, say, fast anaerobic glycolysis. We can take pyruvate, and then convert it to lactate in the presence of lactate dehydrogenase. And these hydrogens would actually be coming from NADH. Okay, so then we can make lactate. So and then we can actually convert it back. Take lactate, same type of or the same basic enzyme, which is lactate dehydrogenase, and convert it back to pyruvate, which that may sound confusing. But let me explain it this way. Well, when I say confusing in that, how can one enzyme push the reaction both ways, right? That can be confusing. And the short answer here is there are different isoforms of lactate dehydrogenase, okay? So for instance, in a more fast twitch muscle fiber type, this reaction is going to be pushed towards the formation of lactate. Okay, that's going to be the preference for that particular enzyme. However, in muscle tissue like heart tissue, or even you could say slow twitch muscle fibers, the reaction here with the isoform of lactate dehydrogenase is to take lactate and convert it back to pyruvate, and then the body can actually take pyruvate on through the Krebs cycle. So you'll want to come back to this slide again once we hit the Krebs cycle piece. I'll hit this topic again, but I figure hitting it a couple times will help reiterate the point here. So there's different classifications of enzymes, and I've kind of started the ones that are probably most important in our conversations here. We've already hit oxidoreductases. Transferases just transfer elements of one molecule to another. So when we put phosphates on a glucose molecule to make, say, glucose 6-phosphate, that's a transferase. There's hydrolases, and they cleave bonds by adding water. And so when a hydrolase is involved, you're going to be breaking things apart, okay, because you're adding water. Isomerases rearrange the structure of one molecule to make another one, okay? So it's not adding anything, it's not taking anything away, it's just rearranging the atoms that are currently making up that particular molecule. Factors affecting enzyme activity. I pulled these from another book, or these figures from another book, but you've probably seen them before. The two main factors that affect enzyme activity are temperature and pH. So I like this particular picture. I think it's from the Powers and Howley book, because it kind of shows you what normal is, and then how tight the range is that allows the enzymes to work optimally. So for instance, resting body temperature is right around 37 degrees Celsius. But the enzyme activity rates actually work best at a little higher body temperature, right? So it kind of highlights the importance of a warm up. So that's pretty important. And similarly, if you're looking at pH, I think the pH at rest is right around 7.2, maybe 7.4, somewhere in there. And then the optimal range here is still pretty tight, right? And so you deviate from normal or homeostasis, then you see both of these lines, whether it's related to temperature or pH, the enzymatic activity falls off markedly, right? So pretty important to understand there. ATP is the universal energy currency, right? And so we are where can we or humans extract potential energy? That's going to be from our food, right? Our macronutrients, and it's conserved within the bonds of ATP. So as we make more ATP through the metabolism of the macronutrients, that's where we can actually release or use this potential energy. Oops. So chemical energy is extracted from macronutrients and transferred in ATP to power biologic work. And again, this is the universal energy source. So I give you a figure here that outlines the parts of an ATP molecule. You have the adenine, ribose. This adenine ribose is adenosine, and then you have your phosphates at the end. You have 1, 2, 3 phosphates. So ATP is adenosine triphosphate, right? ATP, ADP would just have 2 phosphates, and then AMP would have only 1 phosphate or monophosphate. So back to our list here. So ATP is going to power all forms of biologic work, which we've already kind of highlighted, right? Muscle contractions, active transport, anabolic functions. And so ATP is going to be very, very important. So looking at that last point there. So the breakdown of 1 ATP to ADP liberates about 7 kcals of free energy. And so that energy can be used, of course, to power biologic work, but the vast majority of it is actually released as heat. So that's pretty important to understand. And the last point down here says, does not need oxygen, just ATPase and water, right? So to free up that energy, you just need an ATPase and water to hydrolyze that ATP, right? So when we hydrolyze something, it breaks it apart. So in this case, it breaks off that 3rd phosphate that's out here. High energy bond. That's what this little wavy line here indicates, is a high energy bond. So ATP, intramuscular storage, is only about 80 to 100 grams of ATP. So what that means, practically speaking, is that it's really only enough to last events that are only a few seconds long. You're talking about long jump or a standing long jump, maybe a 1 power lift. So that would be the energy source. So what our body needs to do is to be able to replenish these ATP stores with other pathways, either anaerobically or aerobically. So it reiterates the point, ATP is constantly resynthesized predominantly by fatty acids and glycogen. So that's pretty important. Phosphocreatine can also be used for resynthesis of ATP. And so we'll talk more about that, I think, in a subsequent slide here. So here's phosphocreatine. So you may hear about this in regards to supplements of phosphocreatine or creatine phosphate. It really goes by either name. It's another high energy phosphate bond. Notice it has phosphate attached to it. It releases large amounts of energy when bonds between creatine and phosphate are broken. So the good news here is we can store a lot more phosphocreatine than ATP, 4 to 6 times more. Okay, 4 to 6 times more. However, that's still not that much, right? We have enough phosphocreatine on board to basically last in events that last about 10 seconds. So for elite athletes, you're talking about 100-meter dash, something like that, where that resource will be used up, and you're going to have to use another form of or way to make ATP. So this is the basic pathway to make ATP through using phosphocreatine. You have your phosphocreatine, ADP, adenosine diphosphate, that's available. In the presence of creatine kinase, so a lot of times I'll just refer to that as CK, and then you end up with ATP and then the free creatine there. So that's an important pathway to understand. So you'll note the products here. Products here are pretty benign. You're not generating any lactate. You're eventually going to be breaking down ATP, which will generate some hydrogen ions. But for the most part, this is a pretty simple pathway, pretty quick. We can make ATP very quickly to help replenish those free ATP stores. But again, it's only going to last in events that are about 10 seconds in duration. So this is just reiterating the point that ATP is used for lots of things. We need energy to digest and absorb, for circulation, for muscle contractions, to make more protein, for nerve conductions, for glandular secretions. So again, ATP is the universal energy source, so it's used for all those things. Phosphorylation refers to energy transfer through phosphate bonds. So when we're talking about phosphate bonds, we're talking about high energy bonds. And so that's a way to store the energy. And then once we break those bonds, and that's going to release energy. So most of the energy for ATP phosphorylation comes from oxidation of macronutrients, carbohydrates and lipids in particular. As athletes, as people interested in general health, we typically do not want to break down proteins, right? Not too many people come into a weight loss clinic saying, hey, I really want to lose a lot of protein today. It just doesn't make any sense. If people are looking at weight loss, typically they're looking at fat loss, right? They want to lose fat. And one strategy to do that, of course, is dieting. And so meaning caloric restriction, and caloric restriction, of course, means you're taking in fewer calories than the body actually needs to operate that day or to exist that day. And so when you do that, a lot of times you're deficient in carbohydrate, and then the response of the body is to actually break down more protein. And so that's why you'll see a lot of these weight loss clinics, they'll actually prescribe more protein in terms of percentage of daily intake. Compared to a typical diet. So looking at phosphorylation, we are aerobic beings, so a main way that we make ATP is through oxidative phosphorylation. So this synthesizes ATP by transferring electrons from NADH and FADH to oxygen in the electron transport chain. Okay. So the more NADH and FADH we can create through anaerobic glycolysis, through the Krebs cycle, through beta oxidation, the more potential energy that we'll have stored and to be able to transport to the electron transport chain. So you need to get these numbers in your head. When you transfer one NADH to the electron transport chain, you're going to make about 2.5 ATP. One FADH, you'll get about 1.5 ATP, and I'll explain more of that, of why that difference exists later. So the electron transport chain is about 1/3 efficient, okay, at harnessing useful chemical energy. So the rest, about 66%, dissipates as heat, okay. So which explains a lot, right? If we're making a lot of ATP real quickly, well, and it's through the electron transport chain, well, we're inherently going to be losing some of that energy as heat. So cellular oxidation reduction reaction. So it involves the transfer of hydrogen atoms and their related electrons. So the loss of hydrogen is oxidation. The gain of hydrogen is reduction. Remember, if you're gaining hydrogen, you're also gaining the electrons, which reduces your charge, right? Because electrons are negatively charged. Mitochondria contain carrier molecules that remove electrons from hydrogen and pass them to oxygen. So therefore, oxygen is the terminal electron acceptor in the electron transport chain. So the role of oxygen in energy metabolism, so the ability to use the oxygen is dependent on several factors. The first one is the availability of reducing agents like NADH and FADH to bring in the hydrogen, right? And their related electrons. If you can't deliver them, well, then oxygen cannot be the terminal electron acceptor to make water and ATP. You also have to have the presence of oxidizing agent, of oxidizing agent oxygen in this case, in the tissue. So there has to be oxygen availability. So that is going to be reliant mostly on your cardiovascular system to be able to deliver that oxygen to that working tissue. Then you have to have enough enzymes and mitochondria in the tissues to ensure the energy transfer reactions proceed at their appropriate rate. Right, so all these nutrients need to be delivered in adequate time in order to make enough ATP. So intensity and duration of exercise can affect each of these factors, right? So if you're exercising at a high intensity for a prolonged period of time, or just a submaximal intensity for an increased duration, could impact macronutrient selection, could impact the ability to deliver enough oxygen, and could also impact the type of muscle cell or muscle tissue that's contracting, fast twitch versus slow twitch. So energy sources. Sources of ATP formation include glucose derived from liver glycogen, okay, fat and glycogen molecules stored within muscles, so intramuscular triacylglycerol, intramuscular glycogen stores. There could be free fatty acids derived from triacylglycerol in the liver and adipocytes and subcutaneous tissues that enter the bloodstream for delivery to the active muscle. Okay, so once you kind of burn through those resources that are close to the muscle, then it's got to reach beyond that working muscle, maybe from the liver or subcutaneous fat, to be able to supply those nutrients. And then the last one is intramuscular and liver-derived carbon skeletons of amino acids, which is probably something you don't want to do, right? You don't want to be breaking down protein to get at the amino acids in order to have access to the carbon skeletons to make the nutrients that you need, specifically carbohydrate typically. All right, so these are our energy sources. So now we're starting to get into the nuts and bolts of, well, if I can get this to move, not going to work, of bioenergetics. So with bioenergetics, our macronutrients are carbohydrates, fats, and proteins, and we'll focus on those in this class, of course, but I also want you to pay close attention to the micronutrients. There's B3, B6, vitamin C, B9, B6, B12, and B3. Okay, so in terms of carbohydrate metabolism, niacin is very important in carbohydrate metabolism, and fat metabolism, B6 is very important. Then look at all the nutrients that are important for protein. Okay, those are micronutrients. So all very, very important. So if we're deficient in any one of these, not only macronutrients, but micronutrients, that could impact our performance as an athlete, can impact our health just as a generally healthy human being. So here's a figure that you commonly see in a variety of books, whether it's a nutrition-related book or exercise physiology specific. And it's detailing, or at least generally detailing, if that's even possible, the role of the macronutrients, fats, carbs, and proteins in the bioenergetic processes here. So I want to focus you on a few things here. First thing is the importance of acetyl-CoA. Look at all the arrows and how they basically point to acetyl-CoA right here in the middle. We can get acetyl-CoA from a variety of resources, right? We can get it from carbs, we can get it from fats, we can even get it from the breakdown of proteins. So it's a very important molecule. Well, what do you know about carbohydrates? You know, carbohydrates are a preferred energy source. However, we can't store that much carbohydrate, right? So it's kind of a hot commodity. So if possible, the body wants to spare carbohydrate when appropriate, in preference for something like fat. So if we can make acetyl-CoA from fat, from the breakdown of fat through beta oxidation, then that would be preferred, right? That would be preferred. And so looking at protein, look at the flexibility of proteins. After deamination, which deamination basically means taking off that amine group, that nitrogen-containing group on the amino acid, it's pretty flexible, right? We can provide intermediates to make pyruvate, intermediates to make acetyl-CoA, intermediates to go into the Krebs cycle. So very, very important. Preferably we don't use proteins, right? Because we really don't have a reserve of protein. You don't want to consider your skeletal muscle a reserve of protein, right, for metabolism. Probably not good. You don't want to assume your enzymes, which are proteins, are some type of reserve of proteins either. You don't want to have to break those down either. So let's go back here to one more arrow I want to draw your attention to, and that is this arrow from pyruvate to oxaloacetate. Oxaloacetate is a 4-carbon molecule, and it combines with acetyl-CoA with the first step of the Krebs cycle to make citrate. Okay. Again, carbohydrate's a preferred energy source, but we want to be able to spare it where possible, especially during aerobic events, right? So have you ever heard the phrase, quote, fats burn in a carbohydrate flame? So what that implies is if we run out of carbohydrates, then our ability to oxidize or use fats as fuel is compromised. We won't be able to do it as efficiently at minimum, right? So where possible, during an aerobic event, we want the vast majority of our acetyl-CoA to come from fat. What that does is slows down carbohydrate metabolism to the point where the product of anaerobic glycolysis, here is pyruvate, can actually contribute to intermediates in the Krebs cycle, in this case, oxaloacetate. Okay, so that's very important. Why? Because we can make a ton of acetyl-CoA through the breakdown of fats, a lot. But what we may not be able to have enough of are Krebs cycle intermediates. Okay, so we can supplement that with pyruvate. Okay, and so getting back to that phrase, fats burn in a carbohydrate flame, if this supply is shut off or severely diminished, then we're not able to initiate the Krebs cycle. Okay, and so if you ever have some time, look on YouTube for search something like marathon hitting the wall. Okay, this is somebody that's absolutely exhausted their carbohydrate reserves, and they're trying to complete a marathon. So they're going to be stumbling all over the place. They're not going to be able to have good muscular control. They're not going to be able to think correctly because carbohydrates is the preferred energy source for the central nervous system. And so they're going to be all over the place. So, and if you've ever experienced that, hitting the wall, where you've exhausted all of your carbohydrates, you definitely know what that feels like. Energy release from carbs. So, again, carbs are the primary function of carbs is to supply energy for cellular work. It's a preferred energy source. The complete breakdown of 1 mole of glucose liberates about 690 kcals of energy. Okay, so of this, ATP bonds conserve about 261 kcals, with the remainder dissipating as heat. So again, right around a third of the energy dissipates as heat. So when we're looking at carbohydrate breakdown, we can break it down anaerobically and aerobically. Okay, so very, very important because that is unique to carbohydrate for sure. Proteins can go similar routes, but that's somewhat unique, I guess, for the carbohydrates. So with the anaerobic, glucose breaks down relatively rapidly to 2 molecules of pyruvate. So glucose is a 6-carbon molecule. And remember, we have to conserve all the carbons. We have to conserve the structure. So if we have 2 molecules of pyruvate, that suggests that each pyruvate is 3 carbons in length. Okay, so that's important to understand. On the aerobic side, pyruvate degrades further to carbon dioxide and water through the Krebs cycle and the electron transport chain. So with glycolysis, you're going to have glycogen. You can have glycogen metabolism, and glycogen is just a storage form of carbohydrate. You'll have substrate level phosphorylation in the glycolysis. You're going to have hydrogen release in glycolysis, and depending on the needs, you may have lactate formation. So this slide, I begin to show you the importance of the micronutrients and the importance of having some practical examples of how to get those micronutrients in your nutrition as opposed to just some pill someplace. I think that's a pretty important thing to understand just from a practical standpoint. So with anaerobic glycolysis, you're going to see magnesium show up as being very important. And then with magnesium, some sources of that, of course, these are not exhaustive lists. I try to give a vegetable example and maybe a protein example where you can get these micronutrients. So tuna, green leafy vegetables, kale, collards, and spinach. You are going to see a reoccurring theme with these micronutrient selections, okay? So you're going to see green leafy vegetables come up a lot. You're going to see cold water fish come up a lot. Okay, so very, very common. Another one is potassium. You can get potassium in salmon, and then again, green leafy vegetables, kale, collards, and spinach. There'll be one step where we convert a 3-carbon pyruvate to a 2-carbon acetyl-CoA. And notice just this seemingly one step from pyruvate to acetyl-CoA. Look at the micronutrients that are needed. Thiamine, niacin, biotin, B5. All these micronutrients are acting as coenzymes. So imagine if you are not able to take in enough of these micronutrients and how that would impact these enzymatic processes. Then the Krebs cycle and electron transport chain are here. So Krebs cycle, you got niacin, B2, B5, B12, folate, and magnesium. And with electron transport chain or system, you have copper and iron. So look at the recurring themes here again. With niacin, you have tuna, chicken, bacon, and peanuts. Riboflavin, beef, there's green leafy vegetables again. B5, there's tuna again. B12, there's salmon, tuna, soy. Folate, green leafy vegetables showing up again. There's magnesium showing up again. So you've seen magnesium here in anaerobic glycolysis. You've seen magnesium here in the Krebs cycle. So pretty important. Okay. All right, so this is the beginning of the conversation of anaerobic glycolysis. Let's see how many different slides I got on that. Okay, so I'll walk you through this. Now, one common question I get is, how much of this do I really need to know for an exam? And my answer to that is this: you need to be able to tell the story of anaerobic glycolysis. Okay, and so kind of think about it in terms of your favorite movie. So with your, if somebody asks you to describe your favorite movie, you would probably know the names of the main characters. You would know the plot, and you'd be able to describe your favorite parts of the movie and how they're important, those types of things. So first thing you got to know is you probably need to know the jargon, right? You need to know the main player, the players involved, and that would be the intermediates and the enzymes and the products. And so we'll go through all of these today. Now on an exam, I would never ask you to just list glycolysis. That's nice for just for a demonstration of knowledge. But I want you to be able to tell the story of anaerobic glycolysis. Okay. So, and you can ask me more about that during class if you like, or you can email me, of course. But let's just start running through this. So glucose is a 6-carbon molecule. Okay. The first step of anaerobic glycolysis is facilitated by hexokinase. That in particular enzyme predominates in muscle tissue. Some books may highlight glucokinase as well. I think glucokinase is most predominant in the liver, I think. So notice when you go with this first step of anaerobic glycolysis of glucose to glucose 6-phosphate, you're not making an ATP here. You're actually having to burn an ATP, right? And so that's important because that's noted as the energy investment phase. Yeah, and so this other slide shows that too. So we'll get into that one here in a little bit. This particular slide right here in the purple is really the whole anaerobic glycolysis process. But I gave you 2 more slides that break it up into the energy investment phase right here, and then the energy generating or harvesting phase there. Okay. All right, so let's go back to this. So glucose to glucose 6-phosphate, you phosphorylate the 6-carbon, and that's basically all you're doing. Now there's a choice. If the intermediate is required to make ATP through anaerobic glycolysis, it can continue on down through anaerobic glycolysis. If it is not, say right after a meal, that glucose 6-phosphate can actually be stored as glycogen, okay, through glycogen synthase. To break glycogen out of storage and make that carbohydrate available, glycogen phosphorylase can be used to start breaking up the glycogen to provide intermediates for anaerobic glycolysis. Okay, so up to this point, looking at glucose 6-phosphate, you've taken a 6-carbon molecule and you phosphorylated one end. Okay, that's all you've done through hexokinase. Then you convert it to fructose 6-phosphate through an isomerase, where you just rearranged it, right? You rearranged it from a glucose configuration to a fructose configuration. Then the next step, you burn another ATP. You burn another ATP to make fructose 1,6-diphosphate. And again, that's another kinase enzyme. In this case, it's the rate-limiting enzyme for anaerobic glycolysis, PFK, or phosphofructokinase, okay, PFK. So now you have a carbohydrate molecule, in this case it's fructose, that is phosphorylated on the first carbon and the last carbon. Okay, so now we have high energy bonds that are attached to this particular structure. Now what basically happens is it looks like there's two processes going on, but there's not really. It's really just one process that's happening twice. Okay, so literally each of these steps are happening twice. So you take this fructose 1,6-diphosphate, which is a 6-carbon structure, and it's broken in half with aldolase. Okay. Once that happens, now you have 2 3-carbon molecules. And for your purposes, focus on the 2,3-phosphoglyceraldehyde. That's what you have here. Now you start the energy harvesting phase. Once this breaks up into, it looks like 2 pathways, but it's really 1. So with that, you make 2 NADHs, and you make 1, 2, 3, 4 ATP in this harvesting phase. So these are very important, because now these NADHs can go to the electron transport chain, or they can actually be donated in the presence of lactate dehydrogenase to convert pyruvate to lactic acid. Okay? So there's 2 potential opportunities there for the NADH. So first, there's an isomerase reaction with the the isomerase reaction. I can't even pronounce the thing. Let me see if this one's different. Yeah, these are a little bit different. So don't let these confuse you too much. So for instance, this one gives an isomerase here to facilitate this reaction. If you look here, it's different. Okay, the names are a little different. The next step is a kinase reaction, where whenever you see the kinase, I lost my train of thought here. Whenever you see a kinase, there's going to be an ATP involved. Okay, whenever you see a kinase, there's ATP. So hexokinase, in this case, we're burning an ATP. Phosphofructokinase, there's an ATP burned here. Phosphoglycerate kinase, we're making an ATP, so that's important. Glyceraldehyde 3-phosphate dehydrogenase, you're generating an NADH. Okay, so those are important. The last real important enzyme I see, I want you to make sure to know, is pyruvate kinase. Pyruvate kinase down here at the bottom. So pyruvate kinase, again, you're making another ATP to convert 2-phosphoenolpyruvate to pyruvate, and you end up with 2 of those. Okay, 2 3-carbon pyruvate structures. Okay? So I've got 2 more slides here that basically show the same thing. Okay, but it's broken it up into 2 parts: an energy investment phase and an energy harvesting phase. So you're going to have very similar enzyme names here. They may just be subtly different, but what I want you to focus on are the micronutrients I give you. There's magnesium. Magnesium is an important coenzyme for hexokinase, an important coenzyme for PFK. Here's magnesium showing up again with the mutase. Magnesium and potassium for PK, pyruvate kinase. So look at the importance of those micronutrients in these processes. If you're deficient in these, then you need to be able to get that nutrient, preferably from a food source, but you also could have supplements of some kind with some type of pill or something like that. Now we're going to talk about lactate. So if we look back here, lactate can be converted from pyruvate in the presence of lactate dehydrogenase, and of course the hydrogens that come from NADH. Okay? So most of the time when people talk about lactate, they kind of refer to it in a negative context as kind of a metabolic byproduct. Oh, my muscles hurt because I've got lactic acid or lactate in my muscle. It really shouldn't be considered a metabolic waste product. It actually has several functions. So first one is it can be used to make ATP. So that's important, right? It can also be converted back to pyruvate via lactate dehydrogenase, an isoform that's appropriate for that, to make pyruvate, and then the pyruvate can be converted to acetyl-CoA and go on down through the Krebs cycle. It can also be converted to new glucose or glycogen in the Cori cycle. So it's definitely not just a metabolic waste product, right? It's important. It's an important energy source. All right, now we're going to talk about the hydrogen carrier molecules. I've already touched on these previously, but NADH and FADH, look at the importance of the B vitamins, B2, B3. So these are going to be carrying the hydrogens and the related electrons to the electron transport chain in the mitochondria. Okay, very, very important. NADH can also be used to convert pyruvic acid to lactic acid. Okay, so that'll especially happen when you need to make a lot of ATP real quickly in anaerobic glycolysis, because basically what can happen is NADH is created at this step here, glyceraldehyde 3-phosphate to 1,3-diphosphoglycerate. That NADH can go downstream, donate its hydrogens and electrons to pyruvate in the presence of lactate dehydrogenase to make lactate. Then NAD can circle back up and be used again for this step between glyceraldehyde 3-phosphate and 1,3-diphosphoglycerate. So important. The good consequence is you can make more ATP. Maybe the detriment or the bad consequence is you make more lactate, and decrease pH or increase the acidity of the tissue around it, and may slow enzyme activities as a result. Okay. NADH is shuttled to the mitochondria. So any NADH that's created in the electron transport chain, any NADH created in anaerobic glycolysis could be shuttled into the mitochondria. Okay, there's a process for that. So the two main fates of NADH created in anaerobic glycolysis is either one, I've already said this once, used to help convert pyruvic acid to lactic acid, or those hydrogens can be shuttled into the mitochondria into the electron transport chain. So there's a specific transport system called the malate aspartate shuttle that shuttles hydrogens across the mitochondrial membrane into the electron transport chain. So that particular shuttling mechanism is located in the mitochondrial, the electron transport chain is located in the mitochondrial membrane. So there's a video, you can check that out if you like. Now we're on to the Krebs cycle, or the citric acid cycle, or the TCA cycle, whichever name you prefer. I tend to go with the Krebs cycle, so that's what I'll say from here on out. The second stage of carbohydrate breakdown is known as the Krebs cycle. Krebs cycle can use acetyl-CoA from fats and proteins too, but I guess here we're just kind of focusing on carbohydrate. So we know the product of anaerobic glycolysis is pyruvate. Pyruvate can degrade or be further broken down to acetyl-CoA. And the product of that breakdown is carbon dioxide and hydrogen atoms within the mitochondria. Let's see if I've got a step for that. Oh yeah, it's on the next page. We'll talk about it. The acetyl portion of acetyl-CoA joins with oxaloacetate. It's the first intermediate in the Krebs cycle, 4-carbon structure. How many times have I said that? Quite a few. To form citrate or citric acid. So here's the Krebs cycle. So here's pyruvate. Again, remember that's coming from anaerobic glycolysis. We are now inside the mitochondria. That's where the Krebs cycle lives. Okay. And to convert pyruvate, which is a 3-carbon molecule, to acetyl-CoA, you make 1 NADH, you blow off a carbon dioxide, so you can reduce pyruvate from a 3-carbon structure to a 2-carbon structure. Okay, so now you have acetyl-CoA plus oxaloacetate. That's a 4-carbon plus a 2-carbon makes a 6-carbon citrate. So very, very important. So looking at micronutrients, look at the micronutrients that are involved just with converting pyruvate to acetyl-CoA. I think I gave these to you in a previous slide, but here they are again: thiamine, niacin, biotin, pantothenic acid. Then the Krebs cycle: niacin, riboflavin, pantothenic acid, B12, and folate. And I'm highlighting magnesium again here with isocitrate dehydrogenase. IDH is considered a rate-limiting enzyme in the Krebs cycle, so pretty important. So I'll follow the same rule describing the Krebs cycle as I did with describing glycolysis. You need to be able to tell the story of the Krebs cycle. Okay, so part of that is being able to understand the jargon, understanding the intermediates, understanding the products. Okay, so I'm going to give you the products first. Okay, so products of one turn of the Krebs cycle, one turn, you get 1, 2, 3 NADH, 3 NADH, 1 FADH, 1 ATP right here. Okay, very, very important. It's also important to understand that the product of glycolysis, assuming all the carbons from the glucose molecule end up in the Krebs cycle, you end up with 2 pyruvate. Okay, so to break down all the carbons that came from the carbohydrate, Krebs cycle will occur twice. Okay, one for each pyruvate that's generated. Okay, all right, so let's look at a step-by-step process here. So here's oxaloacetate, which is 4 carbons, plus a 2-carbon acetyl-CoA, you get a 6-carbon citrate. Because this is a circle, you know you're going to have to blow off 2 carbon dioxides by the time you get all the way back around to the beginning part of this circle, once you get back around to oxaloacetate. So citrate is 6 carbons. Isocitrate is 6 carbons, but look what happens here. CO2 comes off. That's 6. That means alpha-ketoglutarate is 5. You blow off another carbon dioxide. Succinyl-CoA is 4. Okay, so if there's one molecule that's unique, or one intermediate that's unique from all other molecules in the Krebs cycle, it's alpha-ketoglutarate. It's the only intermediate that has only 5 carbons. Okay, look for similarities in process, look for differences in process. Succinyl-CoA is converted to succinate, succinate to fumarate, fumarate to malate, then all the way back to oxaloacetate. Know the products: 3 NADH, 1 FADH, 1 ATP, 2 carbon dioxides for each turn of the Krebs cycle. Okay, need to know it, got to know it. Here's another video you can tap into if you like, describing that process. And then finally, we're to the electron transport chain portion. So I don't feel like I require a lot of information in the electron transport chain. So, but that's just kind of my opinion. Others may go into a little bit more detail here, but here's my version of the importance of the electron transport chain. So electron transport chain facilitates oxidative phosphorylation in the mitochondria, and so you can kind of see where it lives within the mitochondria. Here's the cytosol, here's the outer membrane, outer compartment, inner membrane, inner compartment. Electrons are removed from NADH and FADH and are passed along a series of carriers to produce ATP. So here's NADH. It docks up with the first cytochrome. FADH docks up with the second cytochrome. Hopefully now you see why there's a difference in the number of ATP that can be produced. Because NADH docks up earlier in the process, or earlier in the cytochrome process, it is able to generate more ATP because it can build up more of a concentration gradient with these hydrogen ions. Okay, so as these electrons are passed from cytochrome to cytochrome, hydrogens are passed across to build up this concentration gradient. FADH comes into the second cytochrome, so it's not able to build up. It doesn't have as much potential energy, and so it's not able to build up as high of a concentration gradient. So hydrogen ions from NADH and FADH are accepted by oxygen to form water. That's why oxygen will be referred to as the terminal electron acceptor. So at the end of this, you make ATP and water. So I pulled this slide, or this figure, from the internet, and I just want you to have some caution when you're searching for stuff online, as hopefully you've all learned that by now because you've all kind of grown up with it. First, I'm highlighting the importance of copper and iron. So maybe you've heard the importance of iron before, especially with red blood cells, right? Red blood cells carry oxygen. Well, it's also important in electron transport chain, okay? Also an oxidative process, right? And then copper is important as well. So if you look at this artist is kind of describing these cytochromes again in the electron transport chain. And then there's the ATP synthase at the end. But if you look at this looks like it's pumping the hydrogen ions to the cytosol. Well, that's not really true or accurate, we'll say. It really pumps it to the outer compartment. It's not pumping it all the way to the cytosol. Okay, so just be careful how you interpret some figures or slides. They may actually be trying to focus on other important parts of the process and then miss other parts of a process. And this is an example of that. Fats, proteins in aerobic metabolism. So if you're looking at fats, when we're talking about fats, typically we're focusing on triacylglycerides or triglycerides. I just kind of shorten it, describing it that way. Triacylglycerides are composed of a glycerol, which is a 3-carbon structure, and 3 fatty acids, which are long chains of carbons. So the metabolism of fats, triglycerides, niacin's important. When we take fatty acids and convert them to acetyl-CoA through beta oxidation, pantothenic acid, thiamine, biotin, niacin are all important. Glycerol is not an important muscle fuel during exercise. It can still be used as a fuel, but it has to go to the liver for processing to either make new glucose or maybe be injected into anaerobic glycolysis. Protein is broken down to amino acids, right? They're the building blocks of proteins. And so the metabolism of protein, you have the micronutrients, vitamin C, folate, B6, B12, and niacin all being important. So protein can be converted to glucose, pyruvic acid, acetyl-CoA, and even Krebs cycle intermediates. So if you go back to one of the first slides, I really showed the flexibility of proteins and being able to be injected into various pathways in bioenergetics. Now focusing on beta oxidation. So beta oxidation is this process of converting fatty acids to acetyl-CoA. So this occurs in the mitochondria. So let's see here. If we're looking at fatty acid breakdown, my bullet points here, we have a breakdown of triglycerides. We're going to release the 3 fatty acids that are attached to it. Fatty acids are then converted to acetyl-CoA to be used as fuel. So let's say you have a 16-carbon fatty acid. Beta oxidation basically bites off 2 carbon chunks of that fatty acid, and then a CoA is attached to that acetyl group, okay, coenzyme A. So acetyl-CoA then, enters the Krebs cycle. It can be used for energy. So I'll give you an example down here. A 16-carbon fatty acid yields about 108 ATP. And so let's see if I can get you to this. So if you envision a 16-carbon fatty acid, in order to bite off 2 carbon chunks at a time, it's going to have to cycle through beta oxidation 7 times. Okay, and with that cycling, you get 1 NADH and 1 FADH for each cycle. Well, because it cycles 7 times, 1 times 7 is 7, 1 times 7 is 7. And then ultimately, you get 8 acetyl-CoA, because if you take 16 divided by 2, you get 8 of them, right? 8 2-carbon acetyl-CoAs. And so we can generate some ATP from that. And so this is a tally that I use to help describe that. So the number of cycles for beta oxidation is equal to N divided by 2, N being the number of carbons, in this case it's 16, divided by 2 minus 1. So it's 16 divided by 2, which is 8, minus 1, which is 7. The number of acetyl-CoA formed is just N, which is, in this case, it's 16, divided by 2, which is 8. Okay, so let's look at this. With beta oxidation, each turn of beta oxidation, I get 1 NADH and 1 FADH. Okay, so looking at that, because beta oxidation has 7 cycles, and I calculated it using this short equation here, I'll end up getting 7 NADH, 7 FADH, no direct ATP from beta oxidation. That's actually a good test question. With the Krebs cycle, remember these acetyl-CoA can now go to the Krebs cycle. For each turn of the Krebs cycle, I get 3 NADH, 1 FADH, and 1 ATP. Okay, so because I'm generating N over 2 acetyl-CoA, in this case it's 8, I'll have 8 cycles of the Krebs cycle. 8 turns or 8 cycles of the Krebs cycle. Because I make 3 NADH for each turn or each cycle, 8 times 3 is 24. FADH, I get 1. 8 times 1 is 8. ATP, I also get 1 for each turn. 8 times 1 is 8. And then I do a total. So 7 and 24 is 31. 7 and 8 is 15. 8 ATP is still 8 ATP. Assuming all these NADHs and all these FADHs go to the electron transport chain, I'll get 2.5 ATP for each NADH, 1.5 ATP for each FADH, so that equals 77.5, and 22.5 plus 8, that's going to equal about 108 ATP from one 16-carbon palmitate fatty acid. Okay, so if I'm looking at 3 fatty acid, you would take that 308 or 108 number times 3. Right, whatever that would be, 324, I guess. And we can do the same thing for glycolysis. So let's review glycolysis. So I'll walk you through this, but you definitely need to be able to explain where these come from. So looking at the aerobic and anaerobic ATP tally for glucose. So with this, we'll start with glycolysis. So the net, I will start with the gross. The gross ATP production for glycolysis is 4 ATP. But because we burn 2 ATP in the initial phases of glycolysis, the net production is 2. Okay, so for one glucose molecule, we get 2 ATP. We don't get any ATP production from oxidative phosphorylation. And so at this point, our subtotal is 2. But we also generate 2 NADHs. And if we assume those NADHs go to oxidative phosphorylation in the electron transport chain inside the mitochondria, 2 times 2.5 is 5. Okay? Because remember, for each NADH, you get 2.5 ATP in the electron transport chain. 5 ATP plus 2 ATP is 7. Okay? So up to this point, we have 7. Once we have our pyruvates from anaerobic glycolysis, remember we get 2 of them, we can convert them to acetyl-CoA. For each pyruvic acid that's converted to acetyl-CoA, we get 1 NADH. Because that happens twice for each molecule, we end up with 2 NADH. So if those NADHs go into the electron transport chain in the mitochondria, 2 times 2.5 is 5 again. 5 and 7 is 12. Okay. Going into the Krebs cycle, this is all going to happen twice, right? So for each turn of the Krebs cycle, we get 1 GTP or ATP, we get 3 NADH, and we get 1 FADH. Because it happens twice, we end up with 2, 6, and 2. So 2 GTP will contribute directly, so 2 GTP or ATP plus 12 is 14. 6 NADHs if they go to the electron transport chain for oxidative phosphorylation. 6 times 2.5 is 15. 15 and 14 is 29. 2 FADHs go into the oxidative phosphorylation of the electron transport chain. 2 times 1.5 is 3. 3 and 29 is 32. So from that one molecule, we end up with 32 ATP. So look at the differences here. 32 versus 108. And most of it's because of the number of carbons that you have, right? And just the size of the molecules, really. There's a difference in ratios, too, of the carbons and oxygens, too, and hydrogens, sorry. Energy released from fat. So stored fat represents the body's most plentiful source of energy. So you're talking about 60 to 100,000 kcals of energy in a male. So we only have about 2,000 or 3,000 calories of carbohydrate. So a huge difference there. So where possible, we need to be able to use this fat to make ATP in order to spare carbohydrate and probably more importantly to spare protein. Energy sources for fat catabolism include triacylglycerol stored within the muscle fiber itself, circulating triacylglycerol in lipoprotein complexes. So think HDL, LDL, VLDL, and even circulating free fatty acids. Those are typically bound to albumin. Cyclic AMP is an intracellular messenger that activates hormone-sensitive lipase. So HSL is hormone-sensitive lipase. So lipases break up fats, okay? Enzymes that break up fat. So when cyclic AMP is activated by a hormone, we'll say epi, norepi, glucagon, or growth hormone, that helps initiate hormone-sensitive lipase to break down fats. Molecules or substances like lactate, ketones, and insulin inhibit cyclic AMP. Okay, inhibit cyclic AMP. So insulin is a hormone that really tells the body to store and build. So if it, in general, tells the body to store and build, it's not going to tell a lipase to work, right? To break down stored resources. So on the bottom here is just a general equation looking at the breakdown of fats. So if you have triglyceride and water, in the presence of HSL, hormone-sensitive lipase, you'll end up with glycerol and 3 fatty acids. Adipocytes. So adipocytes are just that. They're fat. It's fat tissue. So adipose tissues serve as an active and major supplier of fatty acid molecules. Triacylglycerol. Triacyl means 3 fats. Acyl refers to the fats. Then glycerol refers to the 3-carbon structure on the side. Triacylglycerol fat droplets occupy up to 95% of the adipocyte cell volume. Okay, so that makes sense. Most of adipocytes is fat, right? Triacylglycerol. Free fatty acids either form intracellular triacylglycerols or bind with intramuscular proteins and enter the mitochondria for energy metabolism. So in this case, it's a carnitine acyl-CoA transferase. It's a CAT transferase. They'll abbreviate it CAT. Glycerol diffuses readily into circulation. Okay, so then it'll go to the liver for processing. So I forgot about this slide. So there's your fats, maybe stored subcutaneously. They can be put into circulation. Fatty acids bound to albumin and ultimately get to the tissue where the mitochondria is. That's a very Cliff Notes version of that process. That's basically what this is describing. Then the glycerol can be put into circulation and then taken to, in this case, they're showing it going to the working tissue. I guess it could be used there, but it could also be transported to the liver for processing too. Hormonal effects. So we know epi, norepi, glucagon, and growth hormone upregulate or augment lipase activity. It makes more fatty acid available for metabolism. Fat breakdown or synthesis depends on the availability of fatty acid molecules. So it makes more, hopefully it makes sense that if you have more fatty acids available, the body is more likely to use it as a fuel source. So hopefully that makes sense. Hormonal release triggered by exercise stimulates adipose tissue lipolysis, epi, norepi in particular. Initiates or upregulates HSL. Aerobic training increases the availability of free fatty acids for oxidation. So you're more likely to tap into fatty acids as a fuel source early on in exercise, thereby sparing carbohydrate. So that's pretty important. Breakdown of glycerol and fatty acids. So glycerol provides carbon skeletons for glucose synthesis. So here's a triacylglycerol. Here's the 3 fatty acids. 1, 2, 3. Let's count how many carbons there are. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I forgot to count this one. So these are 16 carbon structures. Then this is the 3-carbon glycerol. These 3 carbons on the side here. Fatty acids go to beta oxidation to convert the free fatty acid to multiple acetyl-CoA molecules, which we've talked about earlier. So that process takes these carbons, let me go like this real quick. Assuming that the fatty acids have already been taken off, we'll say, and it cuts these off and puts them into 2 carbon units. So once that happens, keep on cutting these in half. Oops, that one wasn't very good. Once these are all cut in half, then all we need is the coenzyme A on the side of it. And now you have acetyl-CoA that can go into the Krebs cycle. And this kind of highlights that process. Very Cliff Note-ish. There's certainly more of a process with beta oxidation that I haven't given you quite yet. But here's glucose going down through interglycolysis to make acetyl-CoA. But you can also take triacylglycerol, break it up into glycerol and 3 fatty acids, take it to the mitochondria for beta oxidation to make acetyl-CoA as well. Okay, so pretty important. Fats burned in a carbohydrate flame. How many times have I said that expression? So we know oxaloacetate, OAA, can be generated from pyruvate in carbohydrate breakdown. Carbohydrate depletion will decrease or diminish pyruvate and reduces Krebs cycle intermediates and slows the Krebs cycle. Okay, so if you reduce the amount of oxaloacetate you have readily available, it doesn't matter how much acetyl-CoA you have because you can't initiate that first step of the Krebs cycle. So there's a rationale for consuming carbohydrate during prolonged exercise. That's why they've developed things like Gatorade. They've developed other carbohydrate resources during long runs. I think another one's called GOO, but there's all kinds of them out there now. Ketosis, or the incomplete breakdown of fats, could occur during extreme carbohydrate depletion, right? Because fats burn in a carbohydrate flame. If you're basically stopped at the acetyl-CoA step of breaking down the fats, then you could ultimately go into ketosis. Lipogenesis. So up to this point, we've basically been talking about the breakdown of these macronutrients: fats, carbohydrates. Fats and carbohydrates. But of course, we do have the ability to put on fat, right? Put on or create fat, we'll say, through lipogenesis. So lipogenesis is the formation of fat, mostly in the cytoplasm of liver cells. So it occurs when excess glucose, protein, or fat, of course, is not used immediately to sustain metabolism. So it's going to be converted to a stored form of that energy. In this case, it's going to be fat or lipogenesis. Lipogenic processes require ATP energy. Okay, let me read that again. And let me get my finger out here. Lipogenic processes, these are processes that put on more fat, require ATP energy, and the B vitamins, biotin, niacin, and pantothenic acid are required for that. Okay. GLUT4 is a glucose transporter, predominates in muscle and adipose tissue. GLUT4 is important, and you'll hear it mentioned, especially in exercise physiology related topics, because GLUT4 obviously is a glucose transporter, predominates in adipose tissue and muscle, and it tends to migrate to the cellular surface, especially in muscle cells or muscle tissue, when the muscle contracts. And it can respond to insulin as well. So I believe we talked about GLUT4 a little bit previously. If not, we'll get into it later on this semester for sure. Let's see. So energy release from protein. So up to this point, we really haven't spoken a lot about protein, right? And there's a reason for that. We want to conserve protein. We don't really have a reserve of protein like we do carbohydrates and fats. So we know protein plays a role as an energy substrate during endurance activities and heavy trainings. But we don't want to rely on protein as the main substrate. As we deplenish carbohydrate reserves in particular, we tend to pull more from protein reserves, which is not good. So in order to free up the carbons that are within protein or amino acids, there's got to be deamination. So that is going to occur in the liver. Nitrogen is going to be removed from the amino acid molecule. Then there can be transamination. It can be used for transamination in the muscle when an amino acid is passed to another compound. The remaining carbon skeletons can enter metabolic pathways to produce ATP, and I've shown you, I think, at least one or two figures that kind of showed the flexibility of proteins. So pretty important. pretty close to the last slide here. Protein and water. As we break down protein, I probably should have mentioned it in this slide. As we break down protein, we're deaminating that nitrogen-containing group. We can't oxidize it, right? And so we have to be able to urinate it out. And so part of that process of metabolizing more protein is going to mean that we need to take in more water or use more water to be able to urinate out that nitrogen-containing group. So protein catabolism facilitates water loss. I kind of highlighted that just now. The amine group and other solutes from protein breakdown must be eliminated or dissolved in the water. And so this is going to require excretion of the obligatory water as the waste products of protein catabolism leave the body or dissolved in urine. And I kind of highlighted a rhabdomyolysis case. I think this case occurred maybe close to a decade ago. It's kind of interesting in that it was during the initial start of football season. I think this may have been in Minnesota. And the coach thought it would be a good idea if the team pushed one of the sleds around the football field for a prolonged period of time. Well, that turned out to be not such a good strategy because I'm not sure what percentage of the players ended up in the ER with their urine looking like this, what's in this bag. And so basically what happened was there was so much protein breakdown from that particular football-related activity that there was some rhabdomyolysis occurring. And so this is a breakdown of protein or muscle tissue, probably because of the damage. And so it's normal for you to get sore, say after, or so let's put it this way, it's not uncommon to be sore, say after a weight training event. You know, you have some delayed onset muscle soreness, but you can damage muscle to the point where the body's forced to deal with the protein that's been made available, right? And so this was a consequence. So they ended up basically in the ER due to rhabdomyolysis. Another common cause of rhabdomyolysis is compartment syndrome, where it can commonly happen in crush-related injuries, car wrecks, those types of things, where in the particular compartment that was damaged, the pressures, there's so much inflammation that inflammation is not able to be released, and so the inflammation causes more damage, and so the damage causes more inflammation, and inflammation causes more damage, and so I think you can see the problem here. So they have to release that pressure. So I'm sure you can YouTube it. You can see surgical procedures where they actually have to go into that compartment and release the pressure. You know, otherwise they may risk losing that particular leg or that limb or what have you. So as that protein is damaged and the body is trying to deal with that, that can protein and blood and whatnot can come out in the urine. And let's see, one last slide here. So in summary, we just got done talking about the metabolic the metabolic mill. So we're looking at carbohydrates, fats, and proteins in particular, and how they kind of work together to help fuel our bodies. And we also talked about the importance of the micronutrients, right? So we have to have suitable amounts of these micronutrients in order to keep the metabolic mill working the way it should. So we know the Krebs cycle is a vital link between food energy and the chemical energy of ATP. We know the Krebs cycle allows or also provides intermediates that cross the mitochondrial membrane into the cytosol to synthesize bionutrients. And we know that carbohydrates, fats, and proteins can ultimately enter the Krebs cycle or be converted to other molecules. So for instance, carbohydrates can be stored as fat or non-essential amino acids, or converted to non-essential amino acids. Fats can be converted to non-essential amino acids. Proteins can be converted to carbohydrates or fats. So pretty interesting. So hope that helped you. We'll see you in class.